can you call us the survivors?
I don't know what should I call you, right? I should call you the people that attempt to survive. Yeah.
Maybe you should call us the Spartans, no?
Spartans, right.
10 Spartans.
10 or I don't know how many, but yes. That's okay. So again, right, you're preparing for exam 3, exam 2. I will send you by mail over this weekend. So today's topic is antiderivatives. So suppose that what you have to do is you come late to class, as many of you do, and you find that f prime of x, the answer, is 2x. Now the thing is, you want your notes to be complete. What you want to figure out is what was the question. So what was f of x? And this you can do by just guessing, because you have experience with derivatives. And your guess is what?
X to the square.
X squared. Now you know that if you take the derivative of x squared, it will be 2x. But is this the only possibility? Maybe the question was a little bit different. Maybe f of x equaled to, can you give me another example of what it could have equaled to?
It could be plus constant.
Yeah, so let's say x squared plus any constant. You can see that when you take the derivative of a constant, it vanishes to 0. Now, is this the only possibility? That's a big question, right? So keep this question in mind for a moment. Let's say we have now f prime of x equal to, now it's equal to x. What now? How do you guess the antiderivative? What do you do? Well, you would have preferred if the problem looked like this. Because then right away you guess it's x squared, right? Now, if it is 2 here that I placed, I must divide by 2. Now you remember that, well, I hope you remember that the derivative of a constant times the function, I can ignore the constant. I can just take the derivative of the function. So now what is f of x?
One over 2?
No, I mean, so its derivative is x. Let's try it again. You're guessing. How do you guess? So if you got 2x, you guessed x squared. Now, suppose you got x. How do you try to guess what was the original function? Experiment. So take it and say this is x squared. Now take its derivative. It's going to be 2x. So how do I modify this guess to make it correct?
C times x to the c minus 1.
And in particular, in this case,
Just the exponent goes to the
1/2. You see what you do? You modify this 1/2. Now when you take the derivative, the 2 jumps down, cancels, right? Now, of course, more general, it's plus c. Another example. F prime of x is x cubed. The derivative is x cubed. What mechanism could have produced x cubed as the derivative? What is f of x? You understand? If you know derivatives well and how they work, you can think in the reverse. What's the reverse? Right. So you know that derivatives take away from the power of a polynomial. Correct? Derivatives take away from the power of a polynomial. So what you have here is x to the 4th. It's almost like an experiment. X to the 4th, quickly take derivative, 4 jumps to the front. I need to multiply it by 1/4 to cancel out. Correct? Now you try it, and you get x, right? Plus c. Why I add plus c is for now, this is pretty much my best guess. Right? So I know that if I add any constant to the function, the derivative of that constant will vanish. Right? Example. Well, what about in general? Suppose I have that the derivative is x to the power of n. Find a formula for what should be f of x. Careful. So first of all, begin with x, right? Begin with x. And what should be the power of x? Bigger than this, right? So n plus 1. And when I drop n plus 1 down, I want something to cancel it. What is that something? Exactly. And then I say plus c. Okay? Now notice there is something about this formula that might make it incorrect. And this is provided that n is not equal to minus 1. Agreed? Provided n is not minus 1. What happens if I have now f prime of x equal to x to the... You see why minus 1 doesn't work? Because if n is minus 1, then this would be dividing by 0. It makes no sense. Now what happens if I have x to the power of minus 1? What is the antiderivative there? Antiderivative is basically you're trying to cancel the operation of differentiation. You're trying to go back. Somebody solved a question for you and you just want to find what was the question.
0.
No. If the antiderivative were 0, think about it. What does it mean about the function? Antiderivative is 0 means the particle is not moving anywhere, right? If a function is constant, the derivative is 0, right? So if the derivative is not 0, that means that the particle is moving, or the particle has different slopes, right? Any ideas what it would be? What function gives you? Maybe that will give you a hint. What function has derivative 1 over x? Log, right? Log. So you know a function that does that. You have to know your derivatives pretty well. All right. What about if my function, its derivative is cosine x? What was the original function? The original function, very good. Yeah? Did you think in reverse? Sine. And you can always add c because you know up to a constant, right? The guess is going to be correct. By the way, I yet have to have it explained why maybe there are other functions. Maybe there are some more exotic functions that will give you the same derivative as cosine. Let's see how you fare here now. Suppose f prime of x is sine x. What is f of x now? Right, so you think what will give you sine? Something that is similar to sine. If I take cosine, its derivative is minus sine. So you put an extra minus, and here you have it. Let's suppose now that what you have is f prime of x is equal to secant squared x plus 5x minus 3. Now I'm making it a little bit more complicated to guess. Now what is f of x? So we have sums of derivatives here, right? So we know the derivative of sum is sum of derivatives. So you might try tangent of x. Its derivative is secant. Then what?
X to the 5.
No. How do you get something whose that the derivative would be 5x? Try to guess it. What should that be? 5 halves, very good. 5 over 2 x squared. What you think is you ignore the constant. You look at the x. I know that derivatives take away powers of x. So if I go in reverse, I want to add powers of x, right? So this is now to the power 2. Now this 2, when I take the derivative, has to be cancelled by something. And what should remain is 5. So if you have 5 over 2, that works. You see the idea? It's very natural. What's minus 3 now? And plus any constant. Okay? And by the way, when you think about those problems, I might ask you a problem that is intractable, impossible to solve, right? So just think about it, right? I'm tempted to try to give you something like this. Let's see what you would say. All right, so let's look at possible answers. One sine x to the x power. Now it's in your power to check if it's correct or not. All you have to do is find the derivative of sine x to the power of x. You are supposed to know how to do that. Let's check. Right, so this is equal to
X sin x.
it's equal to e ln. Remember this procedure, right? Of, and the reason you do that is because that allows you to drop the x here, right? E that, and then when I take the derivative here, that would be e x ln of sine x times the derivative of x ln x. So the derivative of that will be ln of sine x plus x. Derivative of ln is 1 over. So then if you take the derivative of x sine x, what you get is, well, sine x to the power of x, you get sine x to the power of x times, in parentheses, ln of sine x plus x cosine x over sine x. All of this is a very long way of saying that wrong. Well, I was not expected. I did not expect this. I expected something else that you will do. Well, I'm sure you will do it at some point. Yes?
What about 1/2 x squared sine
I expected that. I expected people to do it. Now, you see, we look at this x, we take the antiderivative of this part, and then we take the antiderivative of that part, and we put it together. Is that right?
That's not the product rule.
That's not the product rule. Right? Not the product rule. Well, at least you laugh. If I was making you laugh more, maybe you would come. But I've been here too long that I cannot laugh any longer. So it's not at my expense. No, that's not the way you do. So actually, how to solve this is to figure out how to reverse product rule. So for now, we will let it be. For now, we're just gonna think of it like this. How should I say it? Confused. No idea. Let it be like this. So, how about this? You understood why this did not work, right? Product, you see, through sum, we know that the derivative of a sum is sum of the derivatives. But product law is not like this, right? So product law is just the derivative is of the first function, the other intact, plus first function derivative of the second. So that would not work. You can verify by taking its derivative. If you have multiplication of two nice functions, it doesn't mean that the antiderivative is anything nice. Anybody knows what to do now? So if the derivative is 1 over 1 plus x squared, what was the function? Remember what functions you know, right? We have exponential functions. Their derivatives are very similar to the function. We have logarithms. We have trigonometry. And we have algebraic functions. And we have inverse trigonometric functions. That's it. That is a nice attempt, but no. It would be wrong. So you can verify by chain rule. So let's see. One person is saying, because it's 1 over something, so maybe f of x is equal to ln of 1 plus x squared. Let's verify if that is so. Let's do a verification. What's the derivative? The derivative is 1 over 1 plus x squared. Fine. But times the derivative of the inside by chain rule, times 2x. So the answer is no. Another guess.
Yes, arctangent.
Arctangent. That's the right guess.
You have to explain why.
Why? Right, I'll explain why. Although I did explain why at some point, right? So you should know that what's the derivative of arctangent. We did it using implicit differentiation. So remember, if you forget the derivative of arctangent, you do something like this. Y is equal to tangent inverse of x. Okay? So what does it mean? It means apply tangent to me and you'll get x. That's all this means. So I'll do what it instructs. I take tangent of y, and that is tangent inverse x. And what do I get here? What do I get? What did I say this means? Well, inverse is a complicated word. How do I think of it? It tells me apply tangent and get x.
So x.
So yes, I apply tangent, I get x, exactly. So it's x. Now, what's the derivative of this? If I know the derivative of this part, by implicit differentiation, I'll locate the derivative of y. So derivative of tangent is secant squared y times y prime. Remember this? And that's equal to the derivative of x equals to 1. So the derivative of tangent inverse x is 1 over secant squared of tangent inverse x. You remember that? Now this can be simplified. How do I simplify this formula? I draw a right triangle. And I place this as the angle tan inverse x. It means if I apply tangent to this angle, I'll get x. The easiest way that happens is, again, tangent applied to an angle gives you the ratio of opposite to adjacent. So opposite is x, adjacent is 1. Right? Apply tangent, x over 1 is x. You follow me, guys? Ask questions, otherwise what do I do?
Wait, so you took the derivative of tan y?
Well, y prime is the derivative of, so if you look at this side, I just carry this to the denominator. Y prime. Y is tangent inverse. So y prime is what I want to isolate. That's the derivative of tangent inverse. And then I just plug it in. This is derivative of y. This is y prime. This here is y prime. And it's equal to 1 divided by secant squared of y, which is tangent inverse. Now I want to simplify this formula. So I draw a right triangle, I interpret what's tangent inverse. Tangent inverse is an angle. And if I apply tangent to it, I should get x. Now if I apply tangent to an angle, I get opposite over adjacent. Yep.
You plugged in y prime for tan x, and the inverse of tan x.
Right.
But isn't it y? Only, how do you plug in it for y prime when it's not y? Because you wrote y is equal to inverse tan x.
All right, let me just again go again through it slower. The symbol y, it stands for tangent inverse of x.
Yeah.
Correct? So if I apply tangent to y, it's the same as applying tangent to tangent inverse. And that gives me x. Now, this y is really a function of x. It's again, here it is. So implicit differentiation tells me that if I take the derivative here, I get derivative of the outer function, derivative of tangent is secant squared y. Times the derivative of the inner function, y prime. I'm actually only interested in y prime. It's just my way of trying to get there.
And then 1 is because of the
1 is because it's the derivative of x. So y prime is equal to 1 over secant squared y, 1 over secant squared of
Yeah, but then somehow you substituted y prime for tan inverse of x.
no, I substituted y. There is no prime in here.
No, for the on the end.
What is y prime? Derivative of y is the derivative of inverse tangent. To take dy dx is the same as to take the derivative of tangent inverse with respect to x. They are the same thing. Make sense now?
Yeah.
Y and tangent inverse are just the same thing. So when I say y prime, what do I mean here? Derivative of this function. So I have this relation. Secant squared of the function times its derivative is 1. Here, hence is this equation. Now I want to simplify this. The angle tangent inverse of x. Apply tangent to it, and what you get is x. So the easiest way to represent x as a ratio of opposite to adjacent is x divided by 1. Correct? So it's x over 1. Therefore, the hypotenuse is the square root of 1 plus x squared. So looking at this picture, what is secant squared of tangent inverse x? But when it's squared, it's going to be the square root of 1 plus x squared squared, correct? Secant squared is, well, secant is opposite over adjacent. Sorry, hypotenuse over adjacent. And so that would be root of 1 plus x squared, and then I need to square it. So what I get is 1 plus x squared. So therefore, this quantity simply reduces to 1 over 1 plus x squared. Okay? All right. So again, this is all of those here you need to know. You need to know how to take derivatives of inverse trig functions, of inverse functions in general, in terms of, like for example, logarithm ln is the inverse function of e to the x. So if I know the derivative of e to the x, you should be able to find the derivative of ln x, and vice versa. All right, so first observation. So suppose we have that the derivative of some function is f of x. So in other words, we know that capital F of x is an antiderivative of little f of x. Antiderivative means that it's a function whose derivative is this little f of x. That's all it is. It's just you go the other direction. Instead of taking derivatives, you go the other way. So if capital G prime of x is equal to f of x, what is the relationship between G and F? What's the relationship between them?
Is it the derivative, I mean the derivative and antiderivative?
So both of them are antiderivatives of little f. My question is, how similar are they? Right? So what we can do is you consider another function, capital H of x, which is defined to be g of x minus f of x. Then h prime x is g prime x minus capital F prime x. And what's g prime x? In this formalism, g prime x is little f of x.
0?
Exactly, minus little f of x. And that is equal to 0. So you see the derivative of a function is 0. What does it mean about h of x? So h of x is what? Its derivative, exactly, very important. So if you think of the physical intuition here, right? If h represents position where x is time, then the fact that the derivative is 0, it means that velocity is 0. It means that the particle is not moving anywhere. Or if you think of slopes, slope of 0 means that my graph of the function is horizontal, so it's a constant function. So h of x is constant. And that's, by the way, formally you need to apply mean value theorem. And the implication is that g of x minus f of x is constant, which means that g of x is capital F of x plus c. what am I trying to say here? What I'm trying to say here, remember that we were doing this. We were saying, we were guessing one antiderivative and adding a constant. We might have been missing other more exotic functions that have the same derivative. But according to this argument, we haven't. That's the total number of possibilities. Okay? That's enormously important. So this is very important. Should I say why it's important? Maybe not. That's what I'm thinking. Very important, but like for a very common equation, differential equation is, it looks like this. It looks like we have the mass of the object times the second derivative of some function is equal to k times the function. So what this describes the motion of a spring. It describes just how the spring is going to move. Now, suppose you figure out to solve this equation and you figure that x is equal to, so x of t, you figure out to anti-differentiate it, it happens to be x0 times sine of omega t. Okay? So this is one possibility, one possible antiderivative. Is this the one describing the spring motion, or maybe there is some other formula that describes the motion, right? Is x of t describing the correct motion? And this question is pretty much the same as is it the only antiderivative, right? So those are questions where you need to worry that you found some solution, but maybe the solution you found is not applicable to the problem at all, right? It's just some solution, but it's not really solving the problem you started with. Okay? So this tells you that if you find one antiderivative, then all the others are very similar. Extremely similar, just add a constant. Okay? So if you haven't found the right antiderivative, you have found something that is very close to it. But yeah. I'll try. Let's see. I'm going to give easier examples, and maybe you will follow them, right? Because I didn't really show you why and anything about this, right? I just told you that you have, this is like a very common, very easy actually example of a differential equation. There are many others, much less easy. and then you might find a solution, but the question is the solution that you found the only one, right? Maybe it's not, mathematically it's a solution to this equation, but it's not a solution to the problem you were searching to solve. Make sense?
Close enough.
Yes, right. Maybe there is another mechanism altogether. This is not the right mechanism that describes what is happening. It's like almost in a murder mystery, right? The solution is you might just pick the wrong. You might blame the wrong person. Somebody innocent of the crime might be blamed, right? That means you haven't found the right solution, right? So imagine you have some equation that tells you that the criminal is this person, or that person, right? Right? How do I pick the criminal? How do I pick the one solution that has to be the right one? Yeah. Well. Let's do a few more examples, and I'll show you more concretely what that involves. So, examples. So suppose that the derivative is root of x. What is the function? So careful. Let's look at this function.
Oh no, negative, sorry.
So this is x to what power? Root of x is x to what power? 1 over 2. All right, so?
2/3 x.
Right, so the mechanism, if I have x to the power of alpha, is that antiderivative has to be to the power of alpha plus 1. So this is x to the power of 1/2 plus 1 and divided by 1/2 plus 1 plus c, and you can tidy it up a little. So 1 over 1/2 plus 1 is 1 over 3 halves times x to the power of 3 halves plus c. And of course, this is also pretty ugly, so better to write it as 2/3 x to the power of 3 halves. All right, so what about f prime x equal to for sin x plus 2x to the power of 5 minus root of x divided by x. Figure out what to do here.
Isn't the function, the regular one, gonna have like product rules? So
Well, maybe there is a way to avoid it, right? If you have quotient or product rule, right? So for now, figure ways of avoiding them. Okay. Like you look at this equation, there is something you can do to make it very manageable. So for example, what can you do here? You can write this as 4 sine x plus 2x to the power of 4 minus x to the minus 1/2. Just divide by x. Root of x divided by x is just 1 over root x. Right? So this, it's too quick. This is just 1 over root x, which is 4 sine x plus 2x to the 4 minus x to the minus 1/2.
So the 4 sine x, that's not the original function doesn't involve product rule also?
Well, 4 sine x, it's a constant. So what can we do with a constant?
No, like before it had an x, didn't it? That's how it stayed?
Well, when we had x times sine x, that's a product rule. When we have a constant, like 4 times sine x, there is a constant rule. There is like a special version of the product rule when one of the products is constant. So what happens here? So what is f of x? Well, what function gives you derivative for sine x?
Times 4 times sine, so it's
No. What function has sine as its derivative? Cosine. Negative cosine. So what's the antiderivative of 4 sine x?
Minus 4 cosine.
Yeah. And then what? Plus, we have here 2x to the power of 4. What's that?
1/2 x. So fifth power.
All right. X is to the 5th power. So what's the constant? 2/5. And finally, we have minus x to the power of minus 1/2. What happens there?
2x to the
So minus 2 x to the 1/2. And you see, adding a constant gives you the totality of such antiderivatives. Nothing else is possible.
How is it that 4? Oh, okay, so
Because the derivative just 4 factors out of the derivative. When you take derivative of this expression, the derivative just jumps over 4 and takes the derivative of cosine.
okay, but it stays.
Yeah, well, yes. Derivative of a constant times a function is constant times the derivative of the function. All right, so let's try to solve examples where we need to determine the constant c. So we have f prime x is e to the x plus 20 over 1 plus x squared. And we know that the original function, its value at 0, is minus 2. So let's try to find f of x. So how do we proceed? So the general guess is what? Right?
Plus 20x
Plus 20 what?
x.
No. This is 20 over 1 plus x squared.
So 20 times
Tan inverse, right? And then plus c. So let's see what's f of 0. So if I plug 0, I should get minus 2. Here if I plug 0, I get e to the 0 plus 20 inverse tan at 0 plus c. So e to the 0 is 1. Tangent inverse of 0 is this is asking then what should be the angle so that the ratio of opposite of the triangle to adjacent is 0. What's the angle? If you apply tangent to it, you get 0. Tangent of what is 0? 0.
190.
Or 0.
Oh. Sine of
You have to visualize it, right? So what's tangent? Tangent is ratio of opposite to adjacent, right? If I make the opposite really small, adjacent becomes longer. So the ratio is 0. So this is 1 plus 0. So therefore, what is c? Oh, plus c, right? So it follows that c is equal to minus 2 minus 1, so it's minus 3. Here's another example. Suppose that we know that if I take two derivatives of a function, I get 12x squared plus 6x minus 4. And I also know that f of 0 is equal to 4, and f of 1 is equal to 1. So my goal is to figure out the original function. So first let's recover the first derivative. The first derivative is what?
4.
So this is x cubed 4 plus 3x squared. And then what? Plus c, right? Now we need to find another antiderivative. So what's f of x? Right? 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 Plus?
One.
This is some number, c. So what's the antiderivative? Cx. And then what? And then there is another constant plus d. Right? So this is just some number. I don't know what it is, but let's pretend it's 7 or something. So that would be 7x. And then I need another constant. Okay? So that's the function. I just don't know what is c and what is d. So that's where I use the fact that f of 0 is 4 and f of 1 is 1. So here I write the equations. 4 equals f of 0. Now what's f of 0? Everything is 0 except for d. So d is 4. Right? And then I write the equation that 1 is equal to f of 1. Now what's f of 1? It's 1 plus 1 minus 2 plus c plus d, which is 4. Right? So it's really, this is c plus 4. Correct? So that means what is c? So c is equal to negative 3. And therefore, f of x is equal to x to the 4 plus x cubed minus 2x squared minus 3x plus 4. Okay? So here is so we have particle with yet unknown position function u of t. We want to determine this. We know that acceleration a of t is 60 plus 4. And we know that the velocity at 0 is minus 6 centimeters per second. And we know that position at 0 is equal to 9 centimeters. So the particle is moving in a straight line. It's moving on a straight line. Find P of t. And that's what I mean. You see where those constants come in, right? That's what I mean. There are possibly, we might find one possibility for P of t, but maybe there are many others, right? So that fact that all the antiderivatives are very similar helps us figure out exactly what P is.
Acceleration is the first derivative of the P of t.
What's acceleration? How do I get acceleration from position?
It's the first derivative of S of t. Just
Well, there is no S. There is A and V and P. So what do you mean?
I know that acceleration would be the first or the second derivative of some other expression of movement.
And of what? What do derivatives do? They measure rate of change. So acceleration is a rate of change of what?
This is speed.
Or velocity, more precisely, right? Directed speed, velocity. Right? So what do we know? We know that I first need to recover the velocity function. And I know that derivative of velocity. Do you see why derivative of velocity is acceleration, right? Because derivative of velocity is change between two velocities over the amount of time that it took for this change to happen. That's acceleration. Derivative of acceleration is called jerk, by the way. Right? So that's how fast acceleration is changing. So v prime of t is a of t, which is equal to what was that? 6t plus 4? So what is the velocity? 3t squared plus 4t plus c. And you can just very quickly guess what it is, right? It's minus 6. You plug v of 0. And that would be c. And therefore, it has to be minus 6. So velocity is 3t squared plus 4t minus 6. Now, what is position? Derivative of position is the velocity, right? So we'll go again. So what's position?
T to the third plus 2t squared
Right.
Minus t plus constant.
T to the third plus 2t squared minus 6t plus, I used c, let me use d, I guess, I don't know, right? So plus a constant d. And what do I know? I know that at 0 it's 9, right? So what's d? D is 9. I mean, without spending this too much time, right? D is 9. And we have it.
So this chapter is exam 3 already, right?
Yeah,
This one.
exam 3. Yep.
So for exam 3, wouldn't it include the stuff that we learned before? Because that's going to be on exam 2.
No, this is the first topic of exam 3.
Oh, okay. So what did you mean by, I hope you're studying for exam 3?
I hope you're studying. That's what I mean in general.
This exam too?
I'm going to send it by mail. But since we don't have too much time, we lost 2 lectures and we went fairly slowly, I think. So I'll send one exam is going to be a freebie, I think. But final is difficult.
You said you're making the final, right?
I don't know. Maybe I am, maybe I'm not.
When is the final?
You have a review for it, right? You can see, like in my website, if you remember what it is, you can go and see that there are reviews, right? So there's a review for the final, review for exam 2, exam 3, everything is there.
What is the date of the final?
The date of the final, I think, is 25th. 25th, right? 19th is probably the date of the 3rd exam. 19th, regular time. What time on the 25th? Probably regular time, right? Probably regular time. 6 to 8, yeah. Ah, you did, right? So 25th, I'm right.
Yeah.
Yeah, good. Good. All right, so this is just one example. I mean, you go in your book, you find others, right? I mean, if you just think that this is the only example that can be given, that's it, right? All right, let's talk a little bit about Riemann sum. So that's going to be, we're entering a difficult part of integration. So first Riemann sum. And this is first a representation for addition. So suppose you have addition is written as A1 plus A2. And then you write something like this. Plus AN. Another form of this is to say simply sigma and write k equal to 1 all the way to n of a sub k. Okay, so this just what this means is just it's like a loop. First k is equal to 1, write it, then write plus, then k is equal to 2, then k is equal to 3, and you have this loop, and this is what you get out, right? Now notice that the same sum does not have to be represented in this from k equal 1 to n. I could have written, if I wanted to, k starts from 0 to n minus 1, but then this would be ak plus 1. Means exactly the same thing. Because you have the same terms that you're adding. So let's make this sum a little bit more explicit. Let's try to see if you understand what it means. So first of all, write out the sum k equal 1 to 3 of k. Let's begin simple. So what does this mean? What are we adding? So first loop, k is equal to 1. So I write what I write here is the same index k, so I write 1 plus what's the next number? 2 plus 3. Don't evaluate it just now. I just want you to understand the notation. Okay?
Wait, the number of loops is on top of the...
Then the number of loops actually is not just on top. It's just from 1 to 3. That tells you how many loops, right? So let's modify it a little bit and see if you still understand what it is. So you see, those are just terms that you're adding, that there are some functions of the index here. Example Suppose now k is equal to 1 to 4, and what we're adding is 2 to the power of k sine pi k. All I want you to do is just write it out. So see if you understand this notation, that's all. Don't evaluate it just yet. So first is k equal to 1. So what do I write? 2 to the power of 1. You see, this tells you what to do with this index. So if k is 1, you have 2 to that index times sine of what? Pi times 1, or just pi, right? Plus, what's next? 2 to the power of 2. Or I'll write it for now like this, right, so that you see where the index is, right? Where k comes in. Right? Plus 2 cubed sine and plus 2 to the power of 4, right? Sine of pi times 4. Now tell me what is this number. It's a very easy number.
It's 0.
Exactly. Because those things are 0, so the number is just 0. But again, I wanted you to understand what the sum is doing, right? So example, k equal to -1 to 2 of five to the k. What's that going to be? Right, plus 5 to the 1 plus 5 to the 2. Makes sense? So, you see, so this is like a convenient notation to make this easy to write. Example, tell me what this would be now. So here, k is from 1 all the way to 5 of the number -2. See if you understand what it is. So what do we write there? Well, so a few of you say 2, but you forget that what happens is that you put this under addition as long as k loops from 1 to 5. So k is equal to 1. What do you write? -2. Plus, now k is equal to 2. What do you write? -2. Now k is equal to 3. Now k is equal to 4. So that's 1, 2, 3, 4, and 5, right? And of course, sums like this, sums with a constant, are very easy to, you see, it's just really -2 multiplied by the number 5. So -10. Tell me what this is. Tell me actually the sum. K starts from -2, goes all the way to 3 of the number 5. What is that going to be? So that would be 5 repeated this many times. How many times? It's 5 repeated 3 minus 2 plus 1 times.
6 times.
Right. Y plus 1? 0. Well, how should I? When you subtract, right? When you subtract, you remove the last term. So subtraction gives you the difference, right? So you need to add that one term that you subtract. So yeah, in general, if you have k is equal to a, and you run it all the way to b of some number c, that's just c, b minus a, the difference between those two numbers, and plus 1, because b minus a does not count the number a. It counts a plus 1 and onwards, right? So it's going to be like this. Make sense? That's the formula. Now, for later use, we will need to figure out the exact sum of things that look like that. K equal 1 to n of k. This is pretty much 1 plus 2 plus 3 plus for any n, right? This is the top index. So we'll need to figure a formula that gives the sum in a more nice way, in a nicer way. So I'm not sure if this is true or not, but one of the greatest mathematicians that ever lived, Gauss, when he was a young boy, he was sitting in a class where the teacher was rather cruel. And what he made the students do, he made them add numbers like this. 1 plus 2 plus 3 maybe to 100. And of course, many of them, they just carried it out. They just tried 1 plus 2, then plus 3, then plus 4, like 100 or to 1,000, right? And the only person who ever got it right and did it very quickly was Gauss, because he figured out a formula. And that's how he was noticed. Now, how did he figure this formula? Actually, they say that his genius was pronounced even before that. But how can we figure out a formula? So suppose that we have that S. By the way, the other person that figured it out at school, my mother, for example, right? In elementary school. It's not. Yeah, why not? First of all, she's very smart, but secondly, it's not impossible, right? Not at all. If you just think a little bit, you might notice a nice pattern here. If you just think outside of the box. Now S, let's S denote this sum. So let's write S in expanded form. So it's 1 plus 2 plus 3 plus n minus 2 plus n minus 1 plus n. Now there is nothing wrong in writing the sum in reverse. So let's start here n, here n minus 1, here n minus 2, here 3, 2, and 1. What do you observe? You observe that each term in the sum here, when I move to the right, increases by 1 unit. From 1 to 2, from 2 to 3, and onwards. It increases by 1 unit. Here, it decreases by 1 unit. So observe that if I add column-wise, the sum in the columns is the same, right? This is 1, this is n. This grew by 1, this decreased by 1. So the sum in each column is the same. Do you see that? Right? So s plus s is equal to 2s. And what we have here is the sum in the first column is n plus 1. The sum in the second column is this grew by 1, this decreased by 1, also n plus 1. Next, n plus 1. How many n plus 1s do we have?
N.
Exactly, right? We just count them 1 through n. So altogether, this is n times n plus 1. And therefore, we have that s is equal to n plus 1 over 2. We'll need that formula soon. So for example, if I take the sum from 1 to 100 of k, right? So the sum from 1 to 100 will be, according to this formula, the same as 100 times 101 divided by 2. Okay? Later on, we will learn the following sums. I don't have time to explain them, and they are more difficult. There is a combinatorial way of dealing with them, but we end up finding also formulas for the square of the numbers, and that would be, I think, n to n plus 1 times n plus 1, or I think better written n plus 1 to n plus 1 over 6, and summation of k cubed is just n plus 1 over 2 squared. Right? So I might comment on how to find those sums, and next lecture we are gonna use this to calculate some integrals. I guess for today that's all we have time for. Goodbye.